In this video, we're going to look at how to predict the products of precipitation reactions. Now, all of the reactions we're going to predict the products are examples of double displacement reactions, where we swap the cations and anions from each compound. So, we're given potassium hydroxide and magnesium sulfate, and we want to predict what are the products of this potential precipitation reaction. And the reason I say potential is because if both of the products are soluble, then no reaction is going to happen. So once we predict the products, we'll have to look at our solubility rules and determine whether the products are soluble or insoluble. So what I need to do is, given each of my reactants, I need to break it down into their respective ions. So potassium hydroxide, I know that hydroxide is -1. Potassium, when it's an ion, is always +1. So the ions from that first reactant are K plus and OH minus. I can do the same thing for magnesium sulfate. I know that when magnesium forms ions, it's always +2 because it's an alkaline earth metal. So I have Mg2 plus. And then I know that sulfate is -2. So I have SO4 2 minus. And so the products, I'm going to connect the potassium from the first compound with the anion sulfate from the second one. And the same thing with the other ones. I'll have magnesium and hydroxide. And so when determining the formulas of the products, I have to use the charges. I can't use the subscripts from the reactants. As an example, when I combine potassium and sulfate, because potassium is +1 and sulfate is -2, the formula of that compound, I'm going to need 2 potassiums for every 1 sulfate, so it's K2SO4, right? And so notice in the reactants, the subscript on the potassium is 1, the subscript on potassium in the products is 2, because those two things don't have anything to do with one another. I've got to use the charges to figure out what the formulas should be. And I'll do the same thing for the magnesium and the hydroxide. Because magnesium is +2 and hydroxide is -1, I know that my product needs to be MgOH2. So the next step is to determine, are these products soluble or insoluble? So on the next slide I have the precipitation chart. Right, so here are our solubility rules for ionic compounds in water. And I've got our 2 products over here on the right-hand side. So magnesium hydroxide, I've got to look and determine whether it's soluble or insoluble. So I don't see magnesium anywhere in here, but I do see hydroxide. So hydroxides are generally insoluble with a couple exceptions, right? Magnesium is not one of the exceptions, so that means magnesium hydroxide is insoluble. So it's going to be a solid. And I'll do the same thing now for the potassium sulfate. So I can actually look at a couple different places. Both potassium and sulfate are in the chart. All potassium compounds are soluble, so I know this is going to be soluble. I can also look at the sulfates. All sulfates are soluble except with the following exceptions. Potassium is not one of them, so for 2 different reasons, I know potassium sulfate is going to be soluble, so it's going to be aqueous. So if I do my equation, and I have my products typed out here, we know that potassium sulfate, we said, was going to be aqueous. The magnesium hydroxide is insoluble, so it's going to be a solid. And then the last thing I need to do is balance my equation. And so to balance this, I think all I need to do is put a 2 in front of the potassium hydroxide. And so I have predicted the products and balanced this chemical equation. Let's look at one more example. All right, so now I have a compound of iron and nitrate and sodium and chloride. So I've got to figure out what are the ions. Now, iron, we know, has multiple oxidation states because it's a transition metal. So I have to use the anion that it's paired with to figure out what its charge is. We need to know that nitrates are -1. So if I have 3 nitrates, each one is -1, that means the iron must be +3. So this is iron 3 nitrate. So the ions from the first compound are Fe3 plus and NO3 minus. From the second compound, sodium is a metal that I know when it forms an ion is always +1 because it's an alkali metal, and chloride is -1. So I'm going to now, in my products, pair the iron with the chloride, the sodium with the nitrate. And so my products are FeCl3, because iron has a +3 charge, chloride has a -1. So for the resulting compound to be neutral, it's got to be FeCl3. And sodium and nitrate are +1 and -1, so they would form NaNO3. So now I'm going to look at my solubility rules and determine whether my products are soluble or insoluble. So first let's look for iron 3 chloride. So here's chloride in our chart. All common chloride compounds are soluble except for the given exceptions. One of those is not iron, so that means that iron 3 chloride is soluble, so it's going to be aqueous. When I look for the sodium nitrate, for a couple reasons, all common sodium compounds are soluble, all common nitrate compounds are soluble, so sodium nitrate is definitely soluble, so it would also be aqueous. So let's go to the next slide. So both of my products were aqueous. The iron 3 chloride and the sodium nitrate were both soluble. So if all the products are soluble, then I don't have a precipitation reaction, and so the answer to this problem is there is no reaction.